Hello and welcome to our introductory session on hunting with network metadata. I am Matt Pecklick, a special projects lead in our professional services organization, and will be leading the session with my colleague, John Faria.
Hello all, my name is John Faria. I'm a consulting analyst here at Vectra, and I will be running through the threat hunting demo in Recall.
Okay, before we start, a little on the webinar portal. Resources can be downloaded from the widget in the bottom left-hand corner of the webinar app. Questions can also be submitted through the questions dialog box that we will attempt to answer throughout the webinar as they come up. And we will be sharing slide and browser content at the same time during various points within the webinar. You can switch between the slides and John's browser content to get a better view of Recall by clicking on the arrow box in the media player. During this session, we will cover three basic hunting use cases: DCSync, DCShadow, and PCExec. The first use case starts very simple, and the subsequent use cases become more complex. At the end of the webinar, we will supply a link to our repo where we have staged dashboards you can download into your own Recall instance or use as a basis for your searches in your own data lake. Over the years, threat hunting has been portrayed as an exciting or cool activity one can do. Some organizations may view hunting as time not well spent, while others may have requirements to hunt to reduce the risk of risk for cyber insurance or to meet industry regulations. At best, hunting is a tedious endeavor that does not always bear fruit. If that is the case, why should an organization hunt if it is not a requirement? There are some specific benefits to hunting that you may consider. Hunting can help an analyst grow and be more efficient by practicing their investigation skills utilizing network metadata. The act of repeatedly forming and testing hypotheses will not only help an analyst grow, they will also come to understand the environment they work in better, making them more efficient. Hunting can also benefit an organization and is typically a part of a mature, proactive security program. It also provides an opportunity to uncover previously unknown attack surfaces. The experience gained hunting can directly translate into custom detections, which can be published into Detect from Recall. This gives an organization the ability to be proactively alerted when something of interest has been observed. Last, you may identify an adversary that is present in your environment when, that has gone unnoticed by other means. In this webinar, we're focusing on using network metadata to hunt for adversaries. Obviously, network metadata is not the only information source you could use to hunt with, but it does provide some distinct advantages. Detect sensors distill metadata from raw network traffic they are fed. Therefore, assuming a sensor has visibility into attack traffic, there will be corresponding network metadata related to those network attack techniques. Vectra provides 12 decoded protocols plus connection information in their enriched metadata. This metadata represents relative information for identifying network-based attacks, regardless of the OS or the type of system being monitored. Network metadata is less prone to being subverted because it's gathered passively from the network segments or at choke points. Vectra's metadata often can provide a different perspective of an adversary's actions that may not be visible with some other tools, or at the very least, a complementary or corroborated view. Before we jump into our first use case, John is going to walk through a brief review of what Recall is to ensure everyone is familiar with the platform we'll be using for this webinar.
Thank you, Matt. So, as an overview, Recall stores Vectra-enriched Zeek-formatted metadata. For easy adoption, Recall is based upon the open-source Kibana interface. Recall itself is hosted in Amazon AWS, owned and maintained by Vectra AI. At a minimum, Recall contains 2 weeks of metadata in its buffers, though licenses can extend the buffer to contain more weeks of data. The network data is collected by sensors deployed across customer networks. These sensors generally sit upon taps and ingest network traffic. This traffic is sent to detect where Vectra's AI algorithms can generate detections for concerning network behavior. The network metadata is normalized into the Zeek format and enriched by Vectra before being sent to Recall itself. The metadata in Recall is broken out into several streams. There are Vectra-specific metadata streams such as iSession, which is a concatenation of all connections and is essentially an enhanced network flow. Protocol-specific metadata, such as user agents for HTTP traffic, are in their respective protocol streams. For today's threat hunting, we will primarily be using the metadata streams DCE, RPC, Kerberos, and SMB files. Vectra is always working to identify useful protocols to parse for metadata provisions to these streams. There are several fields that are common among all metadata streams. Timestamps, along with source and destination IPs, are great examples. Source and destination host names, as found by Vectra's host identification systems, are some other examples. However, each metadata stream has unique data that is specific to that protocol. A few examples of that are the base object and attributes fields in LDAP, client and service fields for Kerberos, and query for DNS.
In our first use case, we're going to discuss DCSync and how to identify it. A common goal of threat actors and red teams is to obtain highly privileged credentials that will allow them to further their progress towards their end goal. There are many techniques that can be employed to obtain privileged credentials once a foothold is established inside an enterprise. However, DCSync takes advantage of the fundamental operation of a Windows environment to obtain NTLM hashes. The DCSync technique is covered by MITRE number 1003006, which is OS credential dumping. To be successful with DCSync, a credential with the correct permissions is required. Therefore, the usage of DCSync is not typically seen early on in an attack, or if a sufficiently privileged credential has already been compromised that would allow the actor to further their activity towards their end goal. Threat actors or red teams that gain access to an account with the proper permissions can use it to retrieve NTLM hashes directly from Active Directory using Microsoft's Directory Replication Services remote protocol. This provides a distinct advantage compared to directly retrieving the Windows NTDS database, as it relies on a standard protocol already in use by machines in the environment and does not require direct domain controller access. This protocol is accessed by a remote procedure call API called DRSU API. Windows domain controllers and workstations utilize the DRSU API endpoint as part of their normal operation, which can make identifying this attack harder. This endpoint can be restricted by using the replication allow list on domain controllers. However, it would have to be maintained, which can be problematic in larger environments. The stolen hashes can allow further progression by use of various techniques like pass the hash, the offline decryption of weak hashes, or generating of a golden ticket when the ticket granting service account's hash was stolen. Detection may be possible if Active Directory event logs are enabled, specifically event ID 4662 in Active Directory Service Access, which will provide information about machines performing operations with Active Directory within an object's system access control list. However, this type of logging may not be feasible as it can result in a performance impact to the system and therefore may not be turned on. Detection is also possible by hunting network metadata, which can provide a complete picture that is hard to obfuscate. To execute the DCSync technique, the adversary's machine will execute DRS get and see changes to a domain controller. This function call can then return a single or multiple NTLM hashes. To hunt for this activity network metadata, we will want to search through the DRSU API RPC endpoint calls, specifically looking for the DRS get and see changes function. This is a common function to be executed between domain controllers. However, it should never be seen sourced from a workstation. When we find the function DRS get and see changes, it's common for it to be preceded by multiple other function calls, typically starting with the DRS domain controller info function call, which in this case may indicate a tool like Mimikatz is obtaining a list of domain controllers for a specific domain. Subsequent calls access the LSA RPC endpoint, which is the local security authority for domain policy, leading up to a second binding to the DRSU API endpoint from which the hashes are then synchronized. Workstations will execute multiple functions via the DRSU API endpoint as part of their normal operation, such as DRS bind, DRS domain controller info, DRS crack names. So it's common for the DRSU API to be accessed from workstations if it involves those functions. I'll turn it over to John.
Great. Thank you, Matt. I'm sharing my screen now so we can all see the lab environment. This lab environment is also known as Dunder Mifflin's recall instance. So for our search, I'm going to set the time range to be the last 7 days to limit extraneous data and keep the searches as fast as possible. To hunt for DCSync, we are going to use the DC RPC metadata stream. So now we're able to search through all of the DC RPC traffic metadata from Dunder Mifflin's network over the last 7 days. On the left are various fields with information regarding the DC RPC records. By selecting one of them, we can see a quick histogram summarizing the field's trends in the last few hundred records. In order to hunt for DCSync, we want to investigate hosts performing the operation DRS get and see changes like Matt described. So let's navigate to the search bar and search for operation DRS get and see changes. Information from each record can be added to a table instead to help make the metadata easier to read. By expanding the records, we can select fields to add to the table. For this threat hunting, I prefer to focus on the originating hostname itself, the responding hostname, the operations endpoint, and the return trip time. As Matt mentioned, domain controllers are expected to call DRS get and see changes on each other, as this is how they synchronize. For our threat hunting, we want to focus on hosts which are not known domain controllers. We can filter out these host names manually, or because we know Dunder Mifflin's host naming convention is very strict, we can add the originating host names to our search itself by instead typing and not orig underbar hostname wildcard DC 0 wildcard. Immediately, we're able to see some rogue device, pmiller PC, which is performing the operation DRS get and see changes on a known domain controller. Now, we want to get more information on this suspicious device, and we can use recall to gather more information about, for example, who was authenticated on the host at this time. In order to do that, we can pivot into recall's Kerberos metadata stream instead. So to search for Kerberos data coming from pmiller PC, we can change our search and look for Kerberos data, which is originating from that host name itself. Now, instead of looking at the responding host name, the endpoint, or the return trip time itself, we can investigate specifically the client, the request type, further down than I remember, request type's not that important. the service itself, and whether the Kerberos request was successful. Here we can also see pmiller PC itself, or its host account, authenticating on the network. This adds some extra noise and records that we don't necessarily want to focus on, so we can specify and not client wildcard $sign /wildcard. Oh, my mistake. Notice how we have to escape that /, and now we can just see the accounts itself, which are on pmiller PC, and the requests that it is making. If we reverse the time, we can even see in order as the host authenticated itself on the network. pmiller was authenticated on the host. pmiller began getting access to some other network resources, potentially gathering further information. And eventually, we even see the domain administrator authenticating on the account, which would make sense as calling DCSync or performing this attack requires very high privileges. So in summary, using the metadata available in Recall, we have navigated to the correct data, filtered out benign activity, and tracked down what appears to be a compromised DA account and a potential DCSync attack against Dunder Mifflin's network. Matt, back over to you to explain the next attack.
Thank you. For the next use case, we're going to discuss DCShadow, and again, how to hunt for it. DCShadow is similar to DCSync in that this technique requires permissions allowing DRSU API replication, and also it requires the permissions that allow the creation of a fake domain controller. The fake DC contains object attributes that the actor wants to synchronize to the directory. This fake DC then temporarily is added to the directory replication topology and triggers an update to the topology, which then causes replication to occur from the fake DC to the real DC. Subsequently, this information is then replicated to the rest of the network. This technique is identified by MITRE as rogue domain controller, which is number 1207. DCShadow may be considered stealthier as it does not generate log messages related to the information that was synchronized, making it harder to determine what information in the directory was modified by the actor. Similar to the previous use case, actors will want to gain further privilege access. With this technique, actors can modify information in the directory, allowing them to add accounts to a group, modify an account SID history, allowing forge access to other domains, modify the hash of a target account, and more. Because almost any object attributes can be changed, this is a very powerful technique and can even allow an actor to cover their tracks by removing data once a step has been completed. It may be possible to detect DCShadow via logs from audit directory service changes, specifically event IDs 5136 and 5141, which monitor the creation and deletion of AD servers. Hunting for this activity with network metadata will use the same metadata stream as we did for DCSync, the DCE RPC metadata stream. However, since the machine the actor is controlling is behaving as a DC, the directionality of the events will show executed activity from both the fake DC and the real DC. The first thing to search for is a non-domain controller, which we'll call a fake DC, performing the DRS add entry function call towards a real domain controller. This is followed by the fake DC performing DRS replica add towards the same DC. After these calls are made, the real DC will execute DRS get NC changes function call towards the fake DC. Once the replication is complete, the fake DC will execute DRS replica delete towards the DC, and finally the DC will execute DRS update refs towards the fake DC. After this, the real DC will signal other DCs that it has new information, and replication will ensue. Keep in mind that a domain admin level privilege credential will be needed for this technique to work, searching for evidence of such an account being utilized from the fake DC is an important step. If such an account is identified, pivot on the identified account to gather context on how and where that account was being utilized previously. This can lead to identification of abnormal behavior and determining how or where the account was previously compromised. I'll turn it over to John to demonstrate hunting for this technique.
Thank you, Matt. Sharing my screen once again. So we are going to continue using the previous metadata stream, DCRPC, and the same 7-day time frame to hunt for DCShadow. Instead of searching for the operation DRS get NC changes, we instead want to search for records with any operations that fall under DRS add entry or DRS replica add or DRS replica del. And again, these operations are expected from domain controllers at times, so we want to add the condition and not orig underbar hostname wildcard DC 0 wildcard. So now we were able to see the same rogue device, pmiller PC, appears to be mimicking a domain controller further. If we expand one of these records, we can select View Surrounding Documents to see the DCRPC traffic occurring at this time. We can see all of the DCRPC operations, which Matt mentioned, occurred both before and after the RPC attack. If we expand the documents further, we can even see these changes that were pushed propagating between the two domain controllers. To assist with hunting for DCSync and DCShadow attacks in your own network, Matt and I have created recall dashboards to help highlight suspicious DRSU API activity. The first two histograms highlight hosts which are performing the operations specific to these attacks, however, should only be seen from domain controllers. To use this dashboard properly, you would want to filter out the domain controllers from your searches. So we can do that in ours by, again, searching for not originating hostname and then following their naming convention *DC star. In your own network, however, you can list the host names here manually by separating them with ORs, or you could even switch and use the IP addresses of your domain controllers. Ideally, in your network, these histograms should be blank, or they should only list the domain controllers. Any other host which is detected here, such as this pmiller call, should be investigated immediately to determine if the privileged activity is expected. Further down, we have a few graphs and charts which may assist further in finding suspicious activity. The first is a timeline showing the maximum amount of data returned by a DCRPC call for a given time frame. And this one works especially well if we cancel out the domain controllers. So this graph can be somewhat unreliable for detecting DCSync, as there may be various DCRPC calls made within your network that could potentially return a large amount of data, along with the large amount of data that can be returned through DCSync. However, it can still be useful for finding some anomalous or suspicious activity. Experimentally, we found that retrieving a single NTLM hash via DRS get NC changes took several magnitudes less time than downloading the entire Active Directory. So the host's RPC RPTT table shows the return time trip for various DRSU API calls. If you see a DRSU API call which is taking a large amount of time to return, then that indicates there could either be a network misconfiguration or potentially that some host is downloading the entire Active Directory or a large portion of it, which would make sense for this attack, as a host which is mimicking a domain controller does not have access to the full Active Directory. The last graph is a heat map, which compares the amount of sync requests versus the amount of responses. In our lab environment, it's not too populated yet. But the purpose of this graph is to highlight suspicious synchronizations from either malfunctioning DCs or greedy hosts, which are calling various synchronization requests to get information about the Active Directory, but not necessarily responding or being called by other DCs within your network. So that is this dashboard, and do remember when you install it in your network to cancel out any hosts which are expected, to set the time range to whatever time you're interested in, and then to hit save and refer to this dashboard constantly. Matt, back over to you to explain the PCExec attack.
Thank you. Okay, the last use case we'll discuss is PCExec, as John mentioned. The term PCExec represents a tool and a technique that is used for remote execution. MITRE attack coverage of PCExec is provided under multiple T numbers, specifically depending on the action that is being taken. PCExec as an executable is a tool in the sysinternal suite of software written for system administrators over 2 decades ago. The tool itself provides a means to execute commands or software on target Windows machines, allowing for easier remote administration. The PCExec executable contains a Windows service image that loads on the administrative share, and then via the Service Control Manager RPC interface, launches that service. Because of this, SMB needs to be accessible on the target machine, and the available credentials need to have permissions to access the admin share, as well as start the service by the Service Control Manager RPC interface of the target machine. PCExec is still widely utilized by Windows admins, as well as red teams and threat actors who are living off the land or utilizing attack frameworks or toolkits that implement this technique. The term PCExec has taken on the connotation of using the technique sysinternals PCExec employs, and does not necessarily indicate that the sysinternals tool itself is specifically being utilized. If an attack framework is being utilized, dependent on the framework, the executable that is dropped on the admin share may have a unique name. When an attack frameworks are used, PowerShell may also be executed in place of a custom executable if it is already installed on the remote machine. When sysinternals PCExec is being utilized, we would expect to see an executable with the name of, in some form of PCExec or PCExec64 being dropped on the target machine's admin share. Advanced threat actors and red teams often use sysinternals PCExec if they are living off the LAN. Living off the LAN reduces an adversary's footprint, making detection harder by utilizing already present tools for specific functions. The usage of PCExec as a technique is commonly seen with attack frameworks like Cobalt Strike, Metasploit Framework, or Empire, amongst others. Additionally, some standalone tools like Impacket also implement this technique. PCExec can be used to obtain an interactive remote shell, push and launch software, or execute remote tools on the target machine. In any of these cases, PCExec allows actors to move laterally due to its ability to execute code on the remote machine. This technique is commonly used to deploy implants or ransomware, or gain further persistence on target machines. Detecting PCExec can be accomplished by monitoring Service Control Manager logs, specifically event ID 7045 if they are available. In our case, we'll be hunting for this activity in the SMB files and the DCE RPC metadata streams. Hunting for PCExec should start with identifying executables of interest being written to the admin share. After that operation, the creation or starting of a service via the Service Control Manager RPC interface should be identified. The usage of PCExec comes in two flavors, interactive and non-interactive. Interactive allows the piping of information back to the source machine, which provides the output of commands or processes being executed, as well as a fully interactive session with a remote host. Interactive sessions can normally be identified by looking for named pipes that contain names, the names standard in, standard out, or standard error in the SMB files metadata stream. PCExec can also execute software on a remote machine non-interactively, which will not provide any output and will lack these I/O facilities. When software is executed on a remote machine, many times it will be pushed to the remote machine by PCExec itself. The executable normally can be identified in the SMB files metadata stream in this case. If you see files named after tools or software you know are utilized in your environment, this can be a good indication that this activity may be administrative in nature. So I'll turn it over to John to demonstrate a number of use cases at this point.
Thank you, Matt. And I am once again sharing my screen. So the first metadata stream we are going to use to hunt for PCExec is SMB files. Our search is going to be for paths to the admin share, so path : wildcard admin, and we are going to be looking for the write action to this share. And we are going to be searching for any potentially dangerous executable or PowerShell file being written. So, and file name, and we have this regular expression, which will perform the matching for us. And in the likely event that that was mistyped, great. So by observing the fields originating hostname, the file name itself, and the targeted path, we are able to see a bit of a story for what activity was occurring. Now, a question came up for how do you differentiate between administrative behavior and a potential attack. There are a few hints and clues that you can use to look for especially suspicious behavior. However, for a lot of this hunting, as far as what mimics administrative behavior, you're going to need to contact the admins themselves and just clarify, hello, were you using this host to target these hosts? And let's say, hypothetically, for this instance, I've gone ahead and I've reached out to the owner of Branch 1 PC, and I said, hello, administrator, have you gone ahead and are you performing these PCExec actions on this domain controller? And if they answer yes, we can go ahead and filter out that value. So now we can focus on some of the more suspicious hosts. Again, P. Miller is here, along with another originating host, Kali Internal, which is very curious. Looking at the table quickly and reversing by time, we can see that the attack included some unknown payload being delivered to Jay Halpert's machine, Mimikatz being delivered to poor Dwight's computer, along with some other interesting PCExec calls being made throughout the network. So there are two other searches which can be useful for getting even a better picture of what activity was occurring here. To search for the I/O setup between these hosts, we can modify our search in the SMB files metadata to instead look for I/O traffic to the IPC share. So once that search loads, we can explore the I/O channels between, for example, Kali internal and J. Halpert's machine. And we can even cancel Kali internal out, so we can focus on what was being done from P. Miller or where P. Miller was targeting. A third option is to use DC RPC again to search for the remote start of services. So we can pivot over to the DC RPC metadata stream and instead search for any of the operations, either create service or start service. And here we can, again, see the different services being started from various originating hosts and what they were targeting. Now, to assist with navigating through all of these different searches, we've created another dashboard that just puts all of the searches into one single page where you can pivot through all of them without having to type them in individually or try to piece together that mess. So one of the first things that I would be interested in investigating is this Kali internal call. So we can filter for just this value, and it will apply to the entire search across all of the different tables in this dashboard and allow us to see that Kali internal was targeting J. Halpert's PC, that there was some services which were created. This file was, of course, written. We can try researching this file to see if we can find anything on it, although the name does appear to be somewhat randomized. And we can even see that there was some large interactive I/O session with a lot of data being exchanged between Kali internal and J. Halpert's computer. Now, if we want to focus on some of the other traffic, for example, we can see the known administrator, which was being used to perform different administrative activities on this targeted administrative host, B1DC01. But of course, we've taken this data, we've gone to the administrator, and the administrator says, yes, that was indeed me. So really, as far as we should be concerned for hunting for legitimate threats, that part can just be canceled out. But for example, let's say we want to investigate some other host. If we're interested in who was targeting the VIP Michael Scott, we can also filter for just, all of the interesting PCExec related calls that were made towards this host itself. And we can see that it appears PowerShell was run on the host and the service was started. But interestingly, there was no interactions here. So this gives us a little bit more information about what might have been occurring. Perhaps there was some implant which has been delivered now, but the interaction and either the administrative or the potentially malicious behavior was carried out through some other means on the network. So this would be a great example of when you would want to take this potential threat that you found and head back over to detect itself to see if there was any other suspicious detections which occurred at this time. So again, the dashboards are all available on the GitHub page, which will be made available after this webinar. We strongly recommend that you add your domain controllers or known and trusted administrative hosts to the searches, and that you perform the hunts now so that you can find either some anomalous or unexpected behavior and figure out what that is before a real threat occurs. It's important to know what is expected and benign in your network so you can spot those threats when they do pop up. Matt, take us out.
John, do you have a use case that you could highlight where you can uncover the account being utilized to perform the calls in question? Because that could be very useful when trying to identify, obviously whose account was being used.
All right. So,
thank you.
Let's see what we can find. One of the things, of course, we've already investigated P. Miller and the account which was being utilized there. But, for example, if we want to look into Kali internal, then we can pivot back into Recall itself by opening up the Discover tab to start a new search. And we can maybe see if someone authenticated via Kerberos here. And if not, then we can get some information about the targets of that. So again, heading back to the Kerberos stream, and if you all remember this search from before, we were looking for Kerberos traffic originating from Kali internal. Kali internal isn't connected to Kerberos in this environment, but, well, I know for a fact that Michael doesn't log in much. Heading back over to P. Miller, why don't we instead focus on the timings so we can see perhaps who had authenticated at the times that these occurred. Of course, these searches are not specific to the time, but we should be able to expand that out a bit further. Well, all right then. New tabs. Always more tabs. Originating hosts. Great. So these occurred on May 13th at 1500 and 1400. So why don't we focus on this time specifically? Head over to that Kerberos stream. Go operations specifically. We can, of course, see the originating host name. The responding host name is just the DC, which is authenticating the Kerberos traffic. But if we, again, look at client, which is blank for some of these, but we can see P. Miller itself. That's just the host. Yep. Great. So we can see that this all appears to have been done by the user account P. Miller, which is interesting. That either shows us that we're dealing with an insider threat or potentially that P. Miller's account has been compromised. Matt, was there another example that you were curious about?
No, I think that illustrates the process. One thing for the audience to keep in mind is that from an authentication standpoint, the sessions may be authenticated via Kerberos, but they also can be authenticated by NTLM. So the NTLM metadata stream could possibly be a good source of information to determine what account was used to authenticate those calls as well. So thank you, John, for jumping into that. So we do have a couple of questions I wanted to address quickly. The first was, distinguishing PCExec administrative behavior from attack behavior. We kind of talked about that a little bit already, and it's really in the context of how, like what you see occurring in the metadata. So John mentioned, identifying activity, and then basically, going and off and reaching out to the user or the admin to understand, was that something that admin themselves had performed. A lot of these activities, other than DCSync or DCShadow being obviously those specific DRS get and see changes, duress, delete and add volumes, those calls you should never see from a workstation, but the type of activity you would expect to see in the network from PCExec can be challenging to identify whether it is administrative in nature or attack related. So a lot of times, you have context in the file names or the machines that are involved or the accounts that are involved that can help you understand whether it is administrative or not in behavior. But even if it is suspected administrative behavior, definitely recommend following up to ensure that is the case, because if you have a threat actor or a red team that happens to be operating from an admin's host and they've stolen their credential, from a network perspective, there's very little way that you could distinguish between authorized versus unauthorized use in that case. Candace also posted a question regarding the syntax utilized for recall searches. We're going to post two URLs that point to support articles in Vectra's support website that can help provide some additional information. But the syntax itself is actually the Lucene search syntax. So if you go out to any, like Google and Google Lucene syntax, you'll find a number of tutorials that can help you understand the syntax that is in use. And then the last question we have from Alex is, is the creation of custom detections. So a lot of the work that John illustrated was showing how to create searches in the various metadata streams, and that those searches can be saved, which can then be enabled as a custom detection that is published back into detect as a detection. So we also have a support article that covers how that is performed within the system and covers those steps. So anything that you can search on, as long as it's sourced from an internal host, can be turned into a custom detection that is then published back into detect. So if there are any other questions, please feel free to post them. We just have a little bit more before we go ahead and wrap up. Okay, so moving on, the last item we wanted to cover is to provide the link to our Vectra GitHub account, and specifically the repo, which is threat hunting dashboards, that you can download the dashboards that John utilized during today's webinar. It is essentially a JSON file that you can download or clone to your local machine, and we've provided a link for instructions that illustrate how to upload into your recall instance. The JSON contains the searches, the visualizations, and the dashboards that were used. So please feel free to download those and use those as a starting point for your own hunting of these techniques. And lastly, before we wrap up, this is the first in a short series of these webinars that we are planning. So we expect to have another session sometime in the summer that covers additional hunting for other attack techniques that you would see in the network. So if there are any suggestions on what we should try to cover, it'd be great if you can post those in the chat. And at this point, unless there are any further questions, I believe we are done. Okay, so I have a suggestion for hunting for beacon hunting. Okay, yeah, we can do that.